Greetings, peeps. Our topic is rotational motion. And I'm going to start with describing some quantities we're familiar with in the linear translational format and then translating them into their angular rotational counterparts. So by now you've done some reading from the text, but I'm going to kind of describe things in a more colloquial, kind of an easier way to understand it, just so we get the concepts down of what these things really are. And the quantity of displacement, symbol is d, unit is m for meters, okay? We call them linear variables because in any one direction, even if that's x or y, they are linear. It's when they combine in two dimensions that we get some funkier shapes like a parabola or whatnot. But each of these could be considered linear. Velocity, v, is measured in meters per second. Acceleration, a, measured in meters per second squared. So their rotational counterparts look very similar, but they've got some funky names. With the first quantity we have is angular displacement. And the symbol for it is theta. We have seen theta before, of course, in right triangle trigonometry. And theta is measured in radians. And I'm sure you're thinking, but I was told to put my calculator in degrees, and you should keep it in degrees. We won't use the trigonometric functions in this class in radians. We will use radians to describe how much something rotates, okay? And I'll describe exactly what this means later, but no worries, we're still going to be using our calculator in degrees for sine or cosine or tangent, but when we make calculations about how much something rotates, we will do that in radians. And rads for short, because we like more rads. Well, I do. I don't mind them sometimes. We've got angular velocity, which is the Greek letter omega that kind of looks like a buttocks, but it's basically a W that's very, very curly, and the units are radians per second. And then we have angular acceleration. Alpha looks like a fishy, and the unit radians per second squared. So what do all of these quantities and variables mean? That's exactly what I'd like to describe very quickly. All right, what is angular displacement? Angular displacement is really the arc length divided by the radius. It's very the technical term. The arc length is s and the radius is r, okay? The basic way of describing this is how much something rotates or turns. And it's measured in radians, okay? Radians are preferred over revolutions because they're linked to circumference, things like circumference in the unit circle. And for example here, the circumference of a circle is always equal to 2 pi r. This part here is actually the angle in radians times the radius. So it's actually an angle of the full circle. The angle, which is maybe something that you would know is 360 degrees, but we mathematically it's consistent with 2 pi if we look at the unit circle. All right. The arc length is really the angle, how much the rotation is in radians as measured in radians times the radius. So you can get any arc length. So for example, yes, if the arc length is 2 pi, it's the full circle. If it's 1 pi, then it's half the circle, pi over 2 quarter circle, okay? There's a convention also in terms of rotation. Displacement is positive for counterclockwise CCW rotation, so that's this direction. So if I rotate like this, that would be considered positive, okay? We're going to stick with this convention, even though, yes, they could be arbitrary. Your book does go with this convention, and that's what we're going to do. Rotations that are negative are considered to be clockwise rotations, and that would be in this direction over here, like so. So theta really is, if I start over here, let's call that the origin of sorts, 3 o'clock, maybe we'll call that the origin. You could start at any moment. And okay, if I rotate that in the counterclockwise direction, it'd be a positive rotation. So the angle at which it rotates is measured in radians. So I just rotated it, we would consider it 90 degrees, but that's really pi over 2. All right, if I continue the rotation, I rotate it pi, 3 halves pi, and all the way to 2 pi. Okay, so this rotation is considered to be positive, and if I flip it around, it's negative. Now, if I spin this really quick, then we would be measuring something called, well, angular velocity. Let's talk about angular velocity. So let's put this away. Got our angular displacement down. Whoa, 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 whoa. You know, I haven't done this with the new microphone yet, so that shit sounds really good. Yes. All right. So what is angular velocity? Before I take out my lights, angular velocity is, this is really the average angular velocity. So it's the buttocks with a kind of a bar over it, like you're bending over? No, I don't think so. Okay. Omega is the change in angular displacement during an interval of time. So we have change in theta over change in t, or the technical way we can do it, we've seen this before with velocity, where it's d minus d naught over t minus t naught. Now we've got theta minus theta naught and t minus t naught. So essentially, what is it? Okay, it's the rate at which an object rotates, how rapidly something rotates. So the faster I rotate this thing, my frisbee, the higher the omega. That's it. Just the higher the speed in terms of its rotation, the higher the angular velocity, there's more omega. Okay, so I can spin this really fast. I'm going to try to do this in front of the camera. Maybe I should do it back here. Now, what you might notice though, cameras are weird. Ever notice that cars in commercials, it looks like their wheels are turning backwards? What's up with that? We're going to study that this week. I will show you exactly why something goes backwards, and has everything to do with the way the cameras work and their frequency, their refresh rate of 30 frames per second. So we'll do some demonstrations of that. So I don't know, as I spin this around, if that, I'm going to check it out later, but maybe that this thing will actually look like the line is going backwards or something weird like that if I do it fast enough. But I'm not skilled enough to do it perfectly in front of the lens, like so. Okay, angular velocity, how fast something rotates. That's the basic gist of it, okay? So that means we got one more, which is, what is, yes, you guessed it, angular acceleration. So it's alpha. That could have been much worse. Oh boy, I think I'd need to have these all set to go rather than put them up. But you know, at least there's no fire. You can tell that things are safe here because you're watching this. Alpha is the change in angular velocity during an interval of time. Omega minus omega naught over t minus t naught. This is like v minus v naught over t minus t naught, the change in omega over change in time. All right, essentially, what is it? The rate at which an objects, should have apostrophe there, of course, like grammar, okay. The rate at which an object's angular velocity changes, how quickly the rotation of an object changes value, okay? So how quickly that omega changes. So suppose your car is at rest and you start off slowly. And as you build speed, the rotations get faster and faster and faster, okay? So as you hit the accelerator, then the wheel begins to change its angular velocity. That's what it is. That's what the angular acceleration is. Now, just like with acceleration, we're only going to deal with constant rotational acceleration. So constant angular acceleration. That's the only thing we're going to deal with. And so guess what? Coming up are some equations that deal with that, and they will look mighty familiar to you. And if you've skipped over to, I think it's page 227, you may have seen them already. They're the counterparts to our regular smileys, but they're the rotational ones. All right, so that's basically it. We have angular displacement, angular velocity, angular acceleration. New stuff for you all about rotational motion and the study of things that rotate, positive, counterclockwise, negative, clockwise. So with that, Morad out.